Good morning, ladies and gentlemen. Welcome to the second day of the Engineers Conclave 2024. Hope all of you are fully recharged after a good night's rest, because we have very exciting talks lined up for you today. The theme of this panel session is DFA in Qualification, Certification and Applications. The session chair is Sri APVS Prasad, Chief Executive, CE, Center for Military Airworthiness and Certification, CENLAC, Bengaluru. There are 6 talks in the session, and the session is co-chaired by Sri S. Ramesh Kumar, Scientist T, DMRL. I request the chair and co-chair to kindly occupy their chairs on the dais. And I request Dr. Venugopal Rao, Adjunct Professor, NIT Varanam, to kindly introduce the session chair.
A very good morning, ladies and gentlemen. It's my privilege to introduce Sri APVS Prasad, Chief Executive, Center for Military Airworthiness and Certification, CENLAC, Bangalore. Sri APVS Prasad, Scientist H and Outstanding Scientist, is an alumnus of Osmania University, Hyderabad. He has obtained BE degree in Electronics and Communication Engineering in the year 1989 and MTech in Telecommunications from IIT Kharagpur during the year 1997. He joined Aeronautical Development Establishment ADE Bangalore in 1990 as Scientist B and has over 30 years of experience in the research and development of avionics systems for unmanned aerial vehicles. He has worked as Program Director of the indigenously designed and developed Mail Rustum 2 UAV, and under his leadership R2 was successfully flight tested. He has created the state-of-the-art aeronautical test facility ATR Chitradurga, which is one of its kind for flight testing of UAVs and other experimental aircraft. His areas of interest are design and development of data links, avionics payloads, software-defined radios, altimeters and Doppler radars. Sri APVS Prasad is recipient of DRDL Lab Scientist of the Year Award for the year 1998, DRDL Team Award consecutively for the year 2004 and 5, DRDL Scientist of the Year Award for the year 2016 and Technology Group Award for 2012 and 2017. He is the Chairman of Aeronautical Society of India Bangalore branch. He is an active member for various prestigious professional bodies such as Institute of Electronics and Telecommunication Engineering and ASCA. He is the Chairman of the Aeronautical Store Standardization Committee. He is also Vice President of the Aeronautical Society of Quality and Reliability. He is CE CENLAC since 31st May 2019. As CE CENLAC, he is overseeing the airworthiness and certification activities of aircraft, helicopters, UAVs, airborne stores, integration of weapons, upgrade programs, indigenization, etc. undertaken within the country for defense services. Under his dynamic leadership, the Airworthiness Policy Document DDP Mass 2002 was revised after a gap of 18 years to keep up with the current industry requirements, and the same is revised further as Indian Military Airworthiness Certification Procedure (IMAC) in quick succession and got approval of Honorable Raksha Mantri. And he is assisted by co-chair Sri Ramesh Kumar, who is heading the Additive Manufacturing project at DMRL. So with these few words, I hand over the session to the session chair, Sri APVS Prasad. Sir, thank you.
Good morning to all. It's a matter of pride and honor to be chairing this session. We look forward to all the 5 presentations. Now I request and welcome the first speaker.
Good afternoon. Thank you, Mr. Ramesh, Dr. Ramesh, for the kind introduction. It's really invigorating for me to connect with the DRDO and the INA community
In this presentation for about 15 to 20 minutes, I would like to explore the ever-enlarging portfolio or landscape of opportunities connected with metal with specific focus on a technology with which I have been directly associated, as polymer fusion. Equally compelling is a reason or a need to explore multitudinous functional challenges one faces while applying this technology, assimilate all that information, and reactively or proactively work on the possibilities of surmounting the challenges. I had an opportunity as well as a privilege to work in academic research as well as laboratory context, and as mentioned, between 1983 to 2013, I was with GTRE, set up the lab in 1999. Post that, I worked in a few academic institutions and also a private company. And whatever I'm going to present today is primarily founded on the insights that I gained in these teams in multifarious contexts. As Dr. John talked about, additive manufacturing today is not the fiefdom of only manufacturing or mechanical engineering community. It's actually become a confluence or interplay of many disciplines. In fact, if you were to look at some of the contemporary PhD and postdoctoral work from computer science department in many IITs and NITs, you see them, they're closely connected with optimization or process outcome enhancement connected with additive manufacturing. That's a kind of versatility these systems are brought in, these processes are enabled, and whether you are talking about unmanned vehicles or gas turbine engines or monolithic rocket engines, we see additive manufacturing being talked about in high esteem. What I want to mention on a side note, anecdotal reference, but very important, is democratization. Whatever may be the complexity of the system, it could be a multinational company or MSME unit or a startup. Today, they are thinking about going beyond the normal by virtue of this technology. Very inspiring case studies from Skyroot and Agricola Cosmos, which were extremely successful in using the technology for monolithic rocket engines. A point of reference for all of us is 3 days ago, a small company which is into the 3D printer supply as well as services entered the public issue market. The company is just about 6.5 years old. It's called Both 3D. To the great surprise of many people like us, aficionados of AM, the public issue was oversubscribed by 315 times. So that indicates the humongous interest which companies and which enterprises have got on the technology of 3D printing. I'm talking about an Indian company, started in Mumbai 7 years ago, focusing only on 3D printing services and missions, have been able to garner that kind of attention. Now, the context which I would like to describe is connected with aerospace and defense primarily. And if you were to look at the application journey of NASA, just as a reference, the recent applications talk about bimetals. And as has been brought out by the preceding speakers, large format printing is also one of the most important things with which the evolution can easily be characterized with. And the reason why there is an explosive interest in the applications connected with additive manufacturing is because of the material choices. The kind of applications and their criticality can be easily inferred by looking at one of the early frameworks. If you were to see here, initially the parts that used to be made were mostly confined to those contexts where parts were in the secondary load parts. There is no criticality of the machine, and structural margin is absolutely very large, and you will not have any problem in case the part fails prematurely. But if you look at the recent examples, we are talking about using the mission mode parts with low margins, and especially for the critical applications with the A1 kind of a class with reference to 3D printing related applications. And concomitant to that kind of a phenomena is also the effort which is required with reference to the qualification. Mr. Prasad is more qualified than anyone to talk about it, but if I have to capture it in just about a minute, the companies or enterprises which are into the development of the systems, they start up with category 0 components, which are not very critical with reference to the load parts, and slowly and steadily they gain confidence in the behavior, in the designs, and we start looking at higher categories where we are talking about parts like nozzle guide vanes and turbine blades, etc., etc. Equally, the interesting thing is the category N, where you have an opportunity to revisit and repurpose the design and try to fulfill the functionality in much superior manner. And whenever we are talking about this kind of designing for additive manufacturing or repurposing the design, you can definitely see that the effort which is involved in manufacturing or realizing the physical artifact could be X, but the effort which is involved, which is connected with proving out and certification could be 10x. So the effort for testing and proving out is one of the very important things when we are looking at the possibility of applications. I'll just pick up an example. It's not a dynamic component. In fact, this is one of the very famous case studies from Boeing Osprey. It is a military aircraft with VTOL and STOL capabilities. And incidentally, the part which is shown is a hydraulic manifold, which is meant for retracting the landing gear into the aircraft structure. And the part which is shown there is the part which is required for checking the structural integrity evaluation of this, the drag strut actuator, and we are talking about proof pressure, retract pressure, cycle depth, leakage, etc. And you can see the paradigm shift in the way the design looks. Maybe the next slide makes it appear much better. What was original and what is DFAM, they are radically different. But in this specific case, it almost led to catastrophe simply because of the fact that in the inspection, corresponding to the dimensions, it was absolutely okay, but there were some debris which were left in the inaccessible zones, which were found out while they were applying the CT-based inspection towards the very end of the development of this new design. So the challenges which are connected with the DFAM could come and spring a surprise at any stage. Now, Dr. John also talked about the standards, but what is very remarkable is the diversity of standards. We have a category of standards which are connected with the general vocabulary, you have process-specific standards, you have material-specific standards, and also application-specific standards. I don't know how many of you are aware, for offshore applications and naval applications, the DRDL has been working very closely with multiple naval agencies in India to come out with the certification portfolio for impellers. And there are a plethora of choices. If you are talking about metal AM, I would like to pick up just two features on the X and Y axis that decide our judgment. One is the resolution and other one is the build rate. So if you were to talk about high volume or high deposition rates, definitely you will have proclivity towards the DED techniques where you can make large parts in limited time. But if you are talking about high resolution parts, we need to think about technologies like laser powder bed fusion. And the central to this particular process is the interaction between the energy source and the metal powder. And continuously, there is the melting and solidification which is happening under the influence of high thermal gradients. And though the energy across the width of the beam varies marginally, that leads to differences in the surface tension, and these surface tension related differences cause turbulence in the melt pool, and the melt pool size is not only influenced by the capillary forces, it is influenced by the surface tension gradients and also inertia forces. Interestingly, the gravity doesn't impact it. That's the reason why you might have seen many case studies where people are talking about additive manufacturing in the microgram. So contrary to what we think, the gravity doesn't impact. And if you were to look at the heat transfer modes at the center, we can see that there is a conduction and reflection, there is a radiative heat transfer from the metal pool or melt pool to the environment, and we are also talking about continuous churning and turbulence within the melt pool, which is leading to the convective heat transfer. So how do you actually approach this particular process while you do not know anything about the behavior of a material in the context of additive manufacturing? So we start plotting these PV diagrams, the laser power on one axis and the scan speed on other axis. And by various permutations and combinations, you can demark 3 different zones wherein if you are applying less energy, you may lead to the lack of fusion. If you apply too much of energy than what is required, you may get into the keyhole regime. And in between, a small space is called optimal process space wherein you can confidently work. But incidentally, the system or the process is much more complex than that. Imagine that you maintain the laser power constant and you are scanning across. Despite the fact that you maintain the laser power constant, just because there is a radical change in the cross section, suddenly there is a peaking of temperature which may lead to the spatter in much excessive manner, leading to the residual porosity. So what do you do in this case, and what are the basic possibilities in terms of doing the experimentation and getting information into the behavior? So we start looking at different parameters like the layer thickness, hatch spacing, peak temperature. Then we are also looking at the specific heat of fusion, etc. and trying to develop these process maps which take into cognizance all the possible variations in the materials and their processability. Now comes a fantastic scenario. As somebody said, it was mostly connected with prototyping initial stages. But if you are able to do the prototyping with a lot of, similarity to the eventual part, which in this case happens to be a quasi-hollow turbine blade, regular process for investment casting of this could be anywhere between 12 to 18 months from the date of design finalization. But if you were to use the metal additive manufacturing and make this turbine blade and spray it with temperature sensitive paints and check up in the heat transfer test rigs, you can get these isothermal plots on the surface which indicate basically the heat transfer distribution on these quasi-hollow surfaces. So this kind of information, which is absolutely valuable, which is only possible after making of the components, can be obtained right in the early stages as long as the conductivity of this material is very close to the conductivity of the material out of which the eventual part is going to be made. Now, this is the reason why, if you were to look at a typical development cycle of a complex aeronautical system, you can see the AM applications in the initial stages, you see AM applications in midway, where you are talking about tooling and design iteration. Also, you can look at the applications of this particular technology in extending the service life selectively depositing the material to extend the lifespan of the part beyond the design life. So what is happening in the recent years is very interesting. In this famous Ashby diagram, we are always interested in materials which have got higher strength at lower density. But at macro scale, we all know there is a coupling of relative density with the macroscopic properties. And if you are interested in this kind of quasi-hollow structures, they are bend-up dominated. But the E by rho ratios are not exceptional. But if you were to micro-architect the parts using the powder bed fusion, instead of bend dominated, they become stretch dominated. And what is the possibility? Enormous. For example, if you were to make this kind of lattice structures, the first one is called conformal lattice, largely surface lattice structure, not much complexity. You can use them readily in the noise suppression context. You go for gyroid, it has got a fantastic feature of becoming support free because it is self-supporting. You can start using for energy absorption, especially in the context of high strain energy. And the last one, the third one on the right extreme, is the customized lattices, where you can talk about mitigating the effect of stress concentration factors and hence the susceptibility to the fatigue failures by going through lattice structures. What's important is initially, let's say about 70 to 80 years ago, if you were to employ this kind of an approach, you had to have one software just for component design, maybe SolidWorks. Then for the lattice creation, you had to go to some other platform. Then after that, you need to do the simulation just to understand how does this quasi-hollow structure behave with reference to the the surface conditions, and finally went into the build file preparation of the system. Now, because of the versatility of the software, you can integrate all the 4 modules into one, and you can complete the activities like this, which I did about 2-3 years ago. You can take the initial and you can employ the topological optimization, or you can apply the principles of generative design, arrive at a part, simulate it, understand the factor of safety, achieve a lot of weight reduction, and also compress the time frame. This is the kind of phenomenal possibility which you are seeing in case of heat exchangers. In the specific case where we are talking about super compact, high pressure, high temperature heat exchanger based on the modified Brayton cycle, which is meant for green emissions. And you can see the lattice structures which are they are reminiscent of the human lung structure. They are bionic in nature. And so it's able to reach the temperatures in excess of 1150 Kelvin and 248 bar because of this kind of quasi-hollow nature. We have seen that in any context of the manufacturing, whenever a new technology came in, let's talk about the history of casting or forging. The moment these technologies became prominent, the evolution of material choices also followed them. But if you were to look at what happened in case of additive manufacturing, at least in the initial stages, most of the times we adapted the existing materials depending upon the processability or welding compatibility to the techniques like DED or powder bed fusion. So we are not able to really take the materials and applications to the highest levels or highest thresholds of possibilities because you are working on secondary choices. But in the recent times, you have seen lots of connected, involved work with the material scientists, metallurgists, mechanical engineers, and the computer scientists, where the alloys are getting designed. I am very sure some of the experts might have spoken about it. I will talk about it in just about 30 seconds. To start with, let's take the context of a ternary Ti64, or let's look at material like Inco 718, which has got close to 10 alloying elements. If you want to really explore the possibilities, the traditional empirical processes will throw options in excess of million combination. So what's happening now is you give the input to the softwares which are specifically developed for these instances with reference to the calorimetry, transition points, specific heat, etc. Then you can understand the thermodynamic phase data. And once you have got the phase data, you can apply some application matrices and quickly understand how do they work with reference to the processability as well as the strength. Two primary important parameters. Once you have this kind of information, you can create a design space wherein you are comparing a candidate material with the benchmark alloys, which could be 718 in this case or CM247. And all these things will help you to interrogate a limited number of material choices, and you can clearly see in this specific case, the material which has evolved or the alloy which has evolved out of this interrogation is almost comparable to 718 in strength, but when it comes to creep resistance and oxidation resistance, it is vastly superior. Now, this kind of a complex mechanism used to be very difficult a few years ago. Now, in the recent years, especially for the past 2-3 years, we have seen the synergistic combination of the machine learning approach into the development of the alloys. What's happening in the machine learning approach is, we understand that there are plethora of parameters which can affect the outcome, especially in the case of powder bed fusion. If you are talking about material alone, you have got particle size distribution, you have got specific heat, you have got density, absorptivity. If you are talking about the process, we talk about hash spacing, layer thickness, scan speed, and even if you were to be very conservative and pick up the number of variables that can possibly impact the outcome, it could be in excess of 10 to 12. So what happens in this case is you pick up dimensionless numbers, could be Marangoni number, or Fourier number, or dimensionless hash spacing, and traditional machine learning models require a lot of legacy data, reliable, proven legacy data. Incidentally, we don't have that kind of a luxury in case of most of the materials of additive manufacturing. So what do? You can combine that with the human intelligence which is gained from the physics-based models and also the metallurgy. In the bargain, the machine learning models become sufficiently accurate enough in terms of predicting the hierarchical structures through which you can understand which parameter is impacting in which way. And you can also develop quantitative indices for understanding which are better choices and which are the worst choices. And in the recent months, I have seen that some of the AIM researchers are talking about a RAG approach, that is retrieval augmented generation. What does it mean? See, you have some real-time data which is coming from the process, and you definitely have the legacy data from the machine, provided it's of the same make as what is being used now. And in addition to that, you can have literature data. So you can get the information from this multifarious context, integrate them, and you can make your machine learning models or large language models so very intelligent that if you start interacting in form of a chatbot, it will start generating the information which is relevant to making the part with superior density or less susceptibility to the failure. Yeah, 3 minutes? So there are some limitations with reference to the volumetric energy density approach. For example, what you see, the scan speed is different in so many instances, but VED is same. VED stands for volumetric energy density. And you can also see that there is no consideration of material properties in this specific case. So for facing this kind of a scenario, the laboratories connected with AEM are developing systems with open architecture with a lot of embedded sensors, visual sensors, vibrational sensors, dimensional sensors, chemical sensors, because in this case we are interested in capturing the information as early as possible in the real time. In fact, I did one experiment 2 years ago with the funding from DST in developing one system based on the principles of binder jetting as well as selective inhibition centering. All that we were able to do is integrate some thermal and optical and some gas-based sensors, and we were able to immediately understand what is the combination of process parameters which can lead to development of parts with superior density. We really need to understand that whenever we are talking about bottom bed fusion for strategic context, there is a macroscopic phenomena which manifests in form of the residual stresses as well as a distortion at large scale. You have got microstructural phenomena in terms of the grains and grain boundaries, and you have got mesophenomena which happen because of the small size of the particles which are getting connected with the energy source. So what is the current thrust of the research is, wherever there is an instance of a part, let's say in some zones you want the part to have higher strength, in other zones you want to have a columnar structure with a proclivity to a particular direction. And in these cases, the entire approach can be based on the phenomenological models connected with the growth and nucleation. And you can quickly infer that in the zones where you have got a liquid solid interface velocity at a low level with a temperature which is high, gradient which is high, you can get a columnar structure. The other extreme you get that EPS growth structure. So where does it lead to? Ultimately it leads to, this is only simulation at this point of time, in terms of creating the blades, turbine blades, with anisotropic structure wherever you are interested in high temperature creep resistance, and in the furtry routes you are interested in the isotropic structure because you are interested in the fatigue resistance. So I just want to conclude my presentation by saying that there are a lot of challenges with reference to application of this technology for realizing a complex system, but democratization is something which is very synonymous with additive manufacturing when you are talking about the design realization. Especially a point of gratification for all of us is the emergence of small units in different corners of the country which are able to make complex parts out of exotic material for strategic application. But one thing which is very important is the long lead time or cycles for proving them, for testing it. Thankfully, the agencies like Similac have gone ahead and launched some strategies or missions in terms of inviting the private people into our ecosystem and getting this entire process of certification as accelerated as possible. And though there are plethora of opportunities for seeking the funding in additive manufacturing processes, technologies, and there are many agencies which are developing indigenous systems. I don't know, some of you might have observed, 4 days ago, RRCAT along with a private company launched one DED technology system with a chamber size of almost like 750 mm by 1.5 meter. And VSSC was quickly able to recognize the impact of that particular innovation and got me into long-term contract for supply of 20+ engines. So that's a kind of development which is happening with reference to indigenous systems also, but there is a need for integrating the research outcomes which are coming from these multitudinous sources and guide the upcoming community in terms of taking absolutely contributory challenges for accelerated realization of the defense systems. I would like to sincerely thank INE, specifically Professor Masudan Reddy, who gave me opportunity for getting back into the realm of additive manufacturing in the context of DRDL and other engineering community which has assembled here alongside of the faculty members, and thank you so much for the patience.
A very good morning to all of you. Starting with a few disclaimers. I do have a slightly bad throat, so please excuse any interruptions. Second disclaimer is that it's been a few years since I actually worked on any inspection of additive manufacturing. But very recently, about a year and a half ago, CII and the Ministry of Industry did have a special meet again to focus on additive, where I had a chance to come back and share thoughts and views on what should be the directions for, especially on the topic of inspection and quality control for additive. So I got reconnected. So whatever you see here is more a compilation of open source material. So just wanted to have that disclaimer. I usually start off with acknowledging all my where I laid my foundations, my two institutes of University of Baroda and IIT Kharagpur. The two places I spent my 37 years, IIT Kharagpur and G Research, and last but not the least, past INE chairman, Shri Dr. Baldev Raju, who was my mentor and guru, and started off my career in NDT, which I'm continuing even now, way back in 1984 when I joined IIT. So I'm grateful to all the institutes and of course my mentor for whatever I am today. So when we talk about additive manufacturing, I think a lot has been covered yesterday, so I learned a lot sitting through all the presentations yesterday and the first lecture today also. And obviously, we have seen that it's a challenging topic. It's a challenging topic, very interesting, very beneficial to the industry, but there are so many challenges to be addressed. And one such challenge is on how do we effectively inspect these materials, either post-build or do other in situ monitoring kind of technologies. And so effectively everywhere what comes into mind is how do we assure quality. And as I think the definitions here are variable, but we want to build quality into the product rather than trying to achieve that after the product has been built, which is very, very true for additive manufacturing as also for many of the other materials. So if you look at the highlights, again, a lot of that has been touched about by many people. But if you look at it, the repeatable quality with the same printer, materials and operators, again touched upon by many people, including my previous speaker, guaranteeing the quality in any location under any of the any set of environmental conditions, and so on and so forth. So basically, to ensure again this quality, we have to have these methodologies which support the whole additive manufacturing process, either through in situ monitoring or through post-build NDT or NDE as we call it, to effectively make sure that the quality of the product which we eventually want is achieved. So, but the major factor today is the complexity associated with the inspection, quality control, characterization, and of course evaluation of damage in AM parts, which will start coming very soon as we have more and more AM parts in service, just like we do have the challenges of damage in the conventional materials, conventionally manufactured materials. This again will be a big challenge. And so the complete understanding of the AM product, the process, the microstructure, the stresses and everything becomes very important. So defects, again, not something new, can have a noticeable impact on the microstructure, mechanical properties and quality of these parts. So once again, putting the emphasis on the fact that ensuring either you have a product with minimum defects which can be inspected and then repaired or taken care of is very important. So the AM process and parameters vary for each process, and NDT of AM products are more complicated than of traditionally manufactured products, as you will see in a couple of minutes. So the approach which you is of course the process qualification, which is what name was talked about in the previous speaker. Ensure that general process is controlled, repeatable, and can produce components within quality requirements. And of course, machine powder operator and in the process itself. And then of course, which was touched upon, was the component qualification, that any part can be printed with the quality requirements, given a certain design, build, penetration, etc. And then of course, individual part QC, which has to be done to ensure that every single part is printed within the quality requirements. And if it is not, defects are properly detected. So again, going back to the emphasis of having a good combination of destructive testing, which will obviously get you the properties, a lot of NDT, NDE, in-process monitoring, which will all combine together, eventually give you the kind of product quality which you're looking for. And so this is again kind of the same thing elaborated a little more. The defect sources can have severe impact on the materials and of course on the part itself. And there's a long list of things which is again being talked about by previous speakers yesterday and today. But this itself tells you that we are trying to deal with a lot of different issues. And unless we have the right technology which can address all of these, we will be still in a state of finding out solutions or having less reliability or confidence in the methodology, which we do not know. Especially we are standing here talking about defense and space and aerospace. We just can't afford any of those. So it's very important that each of these are addressed. And just like in the conventional manufacturing methods, for an NDE engineer, the holy grail is when the day when NDE in a completely non-destructive manner can do three things: can detect all defects, can detect and characterize microstructure, and detect and characterize stresses. So the three major nodes of the triangle: defects, microstructure, and stresses. That is what we are struggling with even in the conventional manufacturing methods. And we probably have made great strides. I think we can claim today to be very good as far as defects are concerned in conventional manufacturing. But here, and there we are still working on microstructure and stresses a lot. But here, when we come to AM, we are talking about the struggle being right at the first one, which is defects itself. And microstructure and stresses obviously are much more difficult than defects when we're talking about detection and characterization. And so, how can we do defect control? Obviously, the best is the first one, the green one, avoidance. How can you really do improve the process to whatever methodologies? We are not getting into the details, but if you can do more and more of defect avoidance, obviously, and that is true for both conventional and additive, and you can really, do better off in terms of use. And of course, it has to be purely proactive, and the part is being nearly like that for the certified version, nothing like that. Of course, if you cannot always do this, we are still far away on that. So we always looked at things like mitigation. Okay, how can we have corrective action triggered partway through defect formation? And this is where in situ monitoring and online monitoring, etc. comes in, where we at least either stop the process or get a feedback from the process that something is moving wrong. So this is again mostly partly reactive and partly proactive. And last but is the repair, when you have to take the corrective action post-build. Okay, when the defect has formed and really you do not have much options and then you can do. So really speaking, we are looking at a two-dimensional approach to getting better and better quality in AM. And that is about how do we have better in situ monitoring methods and how do we have better NDE methods, which are inspection methods post the thing. And so this again, many people have talked about it. I won't spend time, but huge number of defects, and this is just a sampling of what we expect and see. And obviously, you cannot, you may, with time, as we understand the AM process better and equal materials much better, maybe we will reach a stage where we will reduce the number of defects which we have today on the list and bring it down to maybe a selective few which are more challenging. But we still have to wait for that. Again, there are defects which everybody is aware of, so don't want to spend time on that. And this is, of course, the cause mode of failure and defect formation in one mode of additive. lead to, and obviously what you see in the red color is what is the final defect which it leads to in terms of either porosity, walling, oxides, unconsolidated powder, and a whole lot of things. So basically there is a strong interplay of how the machine works, what the material is, what the process is, and the parameters, process parameters, which could lead to that. So one way of control which we saw in the previous, avoidance, right? The buzzword is how can we avoid, could be with proper control of the process parameters, which again has been touched upon by many speakers. But irrespective of how well we do, just like in the conventional manufacturing, we will land up with defects. Okay? We still do not have any methodology to completely avoid it, and which means we have to continue building and developing newer and newer technologies, or utilize existing technologies to do better inspections. The biggest challenge which came along with it, especially for the inspection world, is the fact that when you used to make parts differently and assemble them, we had the luxury and liberty of inspecting the individual parts before they went into assembly. But now, with the excellent benefit which we have of AM, of building complex parts, there is a huge challenge of inspection of such complex parts directly. We are limited in the number of methods which can be used to inspect some complicated parts like this. And that's where the challenge of how to do inspection in a better way continues to be addressed by the inspection community. And this is again, just a sampling of various methods which you are aware of and you might already be using, but you do have the entire gamut spectrum of the resolution which you are looking for, from nanometers to millimeters. And there is no single method which can do everything. And so you do have a bunch of different methods which can do in terms of the resolution of the defect you are looking for. On the other hand, we have primarily three types of defects: surface, subsurface, and volumetric. And again, the physics of methodologies allow some of the methods to only do surface, some of them to do surface and subsurface, and some of them which can do volumetric. So depending on the process you are using, depending on the type of defects you are expecting, you will be choosing the right appropriate method, combined with the fact that what is that resolution you are looking for. Again, whole list of methods, again taken from literature, but some of them which are more surface sensitive, some of them are obviously not applicable at all, as you can see here, and some of them, may be applicable kind of thing. Some of them could be through thickness. So you do have a bunch of methods already available, which have been well tested out in the conventional manufacturing methods, but it is not that they can be blindly applied also here because of several of the other complications, especially things like surface roughness, things like the microstructure, which evolves, etc. Makes it a little more challenging when we even apply the conventional methods to any of these conventional things. The other thing is about the design complexity. It is obvious that the biggest advantage of AM has been the fact that we can build complex design parts. And so, I think US Air Force came up with this kind of a classification of 1 to 3, 1 to 5 design complexities, and where there is a line of sight to almost every surface, and only few details are needed, like that's the complexity level 1. 2 is line of sight to most surfaces, to some surfaces, full of details and full of tiny details, and that will determine what NDT method can be applied, right? So that classifying your component in terms of 1 to 5 will also be directly correlated with what methodology can be applied and so on. And that gives you a guidance in terms of how to move forward. And this is again, just an example. Okay, group 1 is the simple tools and components, optimized standard parts. You can see that you have access to all the surfaces. So hopefully most of the ND methods can be applicable and do. But as you go towards 5, complexity 5, you can see it's going to be extremely tricky. That is where the computed tomography becomes one of the most popular methods today for complete complex part inspection in 3D. Again, it was mentioned by my previous speaker the fact that the industry typically works on standards, and unfortunately unfortunately, the number of standards which have actually come up for specifically non-evaluation and inspection is still very, very limited. We do have the ISO 52904 released last year, the new version, and that talks about a couple of methods, not all the methods. Again, and it's more generic in nature. So we really have a very strong need, and when I talk about the recommendations, I talk about that, but really a big need to work on standards. And I think it's a combination of all the industries, be it defense, aerospace, automotive, whoever it is, to form some kind of a consortium, because we need to have a seat on the table, especially wherever standards are being made, be it ASTM, ASME, ISO, BIS, and so on and so forth. And then, of course, one of the challenges with NDE also, as those of you who would have practiced it, would know that we also have to create a lot of artificial blocks. Okay, and that again for the AM process is not very easy. So there is one standard, it talks about intentionally sealing flaws, okay, in metallic parts. So you actually create artificial defects, knowing through using this kind of a standard, and then use that for inspection. Again, just a very quick example, not taken from literature, of how penetrant testing is getting used for AM parts, has its own big challenge because of surface roughness. Okay, penetrant testing, as you know, is applicable only for surface defects which are open to the surface, and that doing it on a very rough surface is very, very, very difficult in some sense. So we need to do all that. And so I'm going to skip some of them, but these are pretty much available in the literature. How this is one of the most popular techniques, phase area ultrasound. It's been around for a few years. How it is being used more and more in additive manufacturing. And of course, this is a very upcoming and very popular method for which they already also have standard called resonance ultrasound spectroscopy, where the whole AM component can be inspected. Spatially resolved acoustic spectroscopy is another popular method, especially for microstructure and texture, which is being invented by a university in UK and is gaining popularity. And of course, I'm going to skip some of them in the interest of time. A lot of CT work thanks to Waygate Technologies, who provided these charts in terms of porosity detection, and of course a lot of work on powder characterization, because just by using CT you can virtually characterize all the characteristics of a powder which you are looking for: output volume, surface area, sphericity, frequency of distribution, and so on. So I'll quickly jump to, I think, what is the main thing I wanted to talk about in the interest of time. Automated hybrid entity methods is there. A lot of use of artificial intelligence, okay, to get better and better parts. So this is probably going to spend a few minutes. So what are the real challenges and gaps which we have seen? The biggest thing, as I already mentioned, lack of standardized procedures for AM. Okay, material specific inspection guidelines, very limited in situ monitoring technologies, complex internal geometry inspection, still very, very difficult, surface finish, quality control, okay, limited computational models for defect detection, lack of, defect itself is not there, so lack of standards for microstructure is very, very far. Residual stress is still very far in terms of the standards and even methodologies to do that. Okay, and of course, when we come back, we find that we again going back to CT as a methodology for inspection. Inspection time and cost is a big thing. As you know, those of you done CT know that it's very time consuming and of course cost. So that is not really the solution in the long term. So we do have to find different ways, either a combination of methods, hybrid of methods, where we do CT only on a specific area and not the entire volume and so on. And of course, limited feedback loops, which again I'll talk about in a few slides, and the whole complexity of the certification process. And last but not the least, which has been touched upon by training personnel. And as you know, in conventional NDT, we have level 1, level 2, level 3 certifications for every method, UT, RTS, and ET, and so on. Now they are very good at forged parts and casts and tubes and pipes and all the traditional stuff. But when it comes to air, who knows? Maybe we need to think of a specific track where we characterize the certified inspectors level 1, 2, and 3 for AM specific parts. Okay, so there are a lot of recommendations. Standardize the terminology for identification of AM anomalies. Okay, standards for the design and manufacture of physical reference standards, image quality indicators, even for CT and RT, digital radiography, you need all of them. Need for a standard guide for the application of NDE to objects produced by end processes. We still do not have something. So industry-driven standard is a very much essential thing. If we really need to see NDE and in situ monitoring progressing along with the fundamentals of AM, which already is making good progress. Okay. NDE acceptance criteria, still we do not have anything, especially for fracture critical AM parts and so on. Develop an industry standard that allows fabrication of subscale test specimens which meet the characteristic defect scale to high structure and other properties. And of course, the STM said that the E07 should address applicability of current and draft CD standards which are already in the works for measurement of internal features, which is dimension. So CD also gives you a lot of dimensional information. So the recommendations more on policy and strategy. I think we need a specific center of excellence on quality control, inspection, and process monitoring somewhere, a consortium of some kind. Invest and promote all stages of the entire PRS, tier 1 to tier 9, and strengthen the infrastructure for testing standard and certification, and enable robust ecosystem to unlock global competitiveness. Okay, obviously, like is a common solution to most problems is to how to bring academia, R&D, and industry more closer and see how we can solve many of these problems. Eventually, we would like to have a smart, effective, efficient, and sustainable ecosystem for AM, where the inspection goes hand in hand with all the advancements in manufacturing and do that. So I got this just 30 seconds. One of the other recommendations are about most of the things being open loop feedback system today, and I think a closed loop feedback system, as more developments in situ monitoring happens, is probably the way to go for the future. So in summary, of course, defense and all the other industries need quality, productivity, reliability, and safety. AM is a rapidly growing technology, and certainly all the enabling technologies, NDE and in situ monitoring, are more an enabler for better AM products. AM defect formation, as we saw, is highly complex, and the complete understanding is still evolving. Almost all conventional NDT methods are applicable, but with limitations. CD seems to be the most popular method currently. However, it is time consuming and expensive and suitable for small parts, but as we go to the thicker parts, it becomes difficult to detect smaller and smaller. Accelerate standard development for greater adoption. In situ monitoring needs greater push and adoption and needs greater interaction, collaboration, synergies between supplier, manufacturer, users, and the NDT inspection QC groups for providing the best solution. Thank you very much.